Hi, I'm Herb Gross, and welcome once again to our Math as a Second Language seminar series. And today we're going to talk about subtracting signed numbers. And right away, I just want to make sure we understand something in terms of vocabulary. Sometimes we'll use the word minus when we mean negative, sometimes when we mean opposite, and this can become very confusing to students. See, let me give you an example. The correct way to, if I read this sloppily, it's minus 8 minus 3, which sounds sort of like a tongue twister. What I should really read it as, this is negative 8. Now I'm subtracting. The word that indicates subtraction is minus. So it's negative 8 minus, and what is this? This is not minus 3, it's the opposite of 3. Remember? So in other words, here's the same symbol used in 3 different ways. And so you can see why language is so important when we're teaching this to the students. And again, notice a little idiosyncrasy I have that you won't see in most textbooks. I do not write a signed number to make this look like, see what some people will do is, for the signed number, they'll say, okay, the adjective part is 8, the noun part is minus, they'll say, and then they enclose this in parentheses to indicate this is one number. So they would write this as minus 8 minus 3, all using minus signs here. And I think you can see that this is kind of a bit disturbing in the sense for a student. How can they all mean the same thing? It's very, very easy for students, especially in algebra. Let me just make a little ad lib over here. Suppose the problem had been negative 8 minus, and now we'll put in a variable over here, say the letter B. People will look at this and they'll say, this must be a negative number because I can see the minus sign here. No, if B, remember we did one of the practice problems? Suppose B was negative 4. The opposite of negative 4 is positive 4. The fact that this is negative B does not mean it's a negative number. The fact that this is the opposite of B does not mean that it's going to be a negative number. The opposite of a number is positive if the number is negative, and negative if the number is positive. Just a very, very important thing to get out of the way before we start. And again, to indicate why it's so important to go back to the basic definition, if you say 5 take away negative 3, see, if you've introduced subtraction as takeaway, suppose there's 5 pieces of candy. How do you take away negative 3 pieces? But you can say the number we must add to negative 3 to get positive 5 as the sum. In other words, don't define 5 minus negative 3 as 5 take away negative 3. It's 5 minus negative 3, which means the number which we have to add to negative 3 to get positive 5. Okay? And again, I think you can see, based on what we did previously, how you would do this, but we'll review it again. In other words, we first want to get from negative 3 to 0, so that means we have to add on positive 3. Why do we want to get to 0? Because it's easy to see what you have to add on to 0 to get to whatever number you want. In other words, what do you have to add on to 0 to get 5? The answer is 5. So what did you add on altogether? Positive 3 plus positive 5 is positive 8, and you have the right to avoid using the plus sign, the positive sign, if the number is positive. And reading comprehension is almost, and maybe even as important as the math itself. You know, one of the reasons I say this is I've seen students who have been taught to key in, looking for key words. If they see the word add, that tells you it's going to be an addition problem. But be careful. If I say, what do you have to add to 3 to get 5? Even though you hear the word add, it's a subtraction problem. What do I have to add to 3 to get 5? The answer isn't 8. The answer is 2. But most students, if they're not careful, will hear that problem as what happens if you add positive 3 and positive 5. In other words, negative 3 plus positive 5 equals blank does not mean the same thing as negative 3 plus blank equals positive 5. In other words, when I interchange the positive 5 with the parentheses, I change the meaning. And the reason that we like zeros and ones is that if you're multiplying any number by 1, you don't change the value of the number. And if you add 0 to any number, or any number to 0, you don't change the sum. So for example, what did we do when we studied fractions? We wanted to know what must we multiply 2/3 by to get 5/7. So the first thing we did was we multiplied by 3/2 to get 1. And once the answer was 1, what do you multiply 1 by to get 5/7? The answer is 5/7. Okay? So altogether, what did you do? You did 3/2 times 5/7. That's 15/14. In other words, you didn't say invert and multiply, but did you notice that's exactly what you did? You took the 2/3 and you inverted it. Why? To get 1. Then you multiplied it by 5/7 to get 5/7. Same thing happened, I said previously. I'm going to keep reviewing this so it really gets locked into your mind. I want to see what do I add on to negative 3 to get positive 5. I first add on positive 3 to convert this to 0. Then I add on 5 more to get positive 5. So what did I add on altogether? Positive 3 plus positive 5. Okay? And so the answer was positive 8. Okay? And again, if you want to see this in terms of a bookkeeping model, profit-loss model, it says, what do I have to do to a $3 loss to convert it into a $5 profit? Okay, and I like this method because you don't see the signs. You see, the negative has been replaced by the word loss, positive has been replaced by the word profit, and now just in words alone and using positive numbers, you have a 3 in the loss column, okay, and you want to wind up with a 5 in the profit column. Well, the first thing you do is what? I can't make a profit until I get rid of my loss. So to offset the $3 loss, I'll make a $3 profit. Now I'm back to even, I'm 0. What do I add on to 0 to get 5? I add on 5. So what have I done altogether? I've added on 3 and 5, that's 8. Okay? And you remember when we talked about whole number subtraction? We talked about the same difference, maintaining the gap. In other words, if the age between John and Bill is 5 years now, any time in the future, any time in the past, as long as they're both alive, the difference in their ages is the same 5 years. So let's look at it in terms of the number line, which is more visual. Finding the gap on the number line, the same difference revisited. Let's again look at positive 5 minus negative 3. So you have one person standing at negative 3, the other person standing at positive 5, and you want to know how far it is for the person to get from negative 3 to positive 5. You want to find this gap and in this direction. And all the add the opposite rule says is, this problem would have been much easier if the person was starting over here. Because it's easy to see what you have to add on to 0 to get whatever number you want. So to get to 0, I had to add on positive 3. Now, to keep the gap the same, if this person moved $3 units to the right, this person at positive 5 also has to move 3 units to the right. That means he started at positive 5 plus positive 3 is positive 8. And so now the distance is what? One person is at 0, the other person is at positive 8. The directed distance is what? Positive 8 minus 0, which is positive 8. In other words, positive 5 minus negative 3 doesn't look like positive 8 minus 0, but it's the same gap. It's the same gap. In other words, just to summarize this sort of briefly, the distance between negative 3 and positive 5, okay, and in fact, that refers to, you can do this with any numbers. I just happen to be working with negative 3 and positive 5. if we view these as points on the number line, the distance between them doesn't depend on the direction in which we move. That is, whether we start at -3 and go to 5, it's exactly the same distance as if we started at +5 and went to -3. In other words, the absolute values. The adjective part is the same. The sign simply determines the direction. So let me show you. So instead of having +5 minus -3, suppose we had -3 plus +5. It says, what do you have to add on to +5 to get -3? Well, again, I mean, the logic is simple enough. I first have to convert +5 to 0, which I can do by adding on -5. And now that now makes this 0. And how do I get from 0 to -3? I have to move 3 more units to the left. So altogether now the answer is what? -5 plus -3, that's -8. And all that means in terms of the number line is previously we said what happens if the guy at -3 moves to 0. This time all we're saying is suppose the guy at +5 wants to get over to -3. Again, he's starting at +5. If he moves 5 units to the left, he's at 0. But to maintain the gap, the person at -3 would also have to move 5 units to the left. That would put the person at -8. So now the answer would be -8 rather than +8. And again, let's just do this with bigger numbers. See, it's not a difficult thing per se, but it's interesting to point out. People like to use pictures. It's fine for small numbers. 3, 5, and 8 aren't going to require you to have an enormous sheet of paper. But when you start working with numbers like thousands, millions, even hundreds, it's kind of awkward to try to visualize the whole thing geometrically. So what the trick is, to use the simple case where you can draw the picture, use that to sort of formalize what it is that's really happening, and then use what's really happening when you have the case of the larger numbers without having to draw the number line. So for example, let's find the direct distance from -123 to +567. Can you visualize you don't really want to put this on the number line? How complicated this will be. Let's go 123 to the left, that will be 1 point. We'll go 567 to the right, that will be another point. It's going to be a pretty big piece of paper, or else you're going to have to use a scale, and it will be hard to tell whether it was 567 or 568. Look how simple it is once you understand the concept. I want to get from -123 to 567. You can think of it in terms of I want to get from a $123 loss to a $567 profit. You can think of it as being 123 feet below sea level, and you want to get to an elevation of 567 feet above sea level. In either case, what you're saying is, if I add on the opposite of -123, to -123, I'll get 0, and if I add 567 onto 0, I'll get the answer. So the first thing we say is what? I'll add on +123 to convert this to 0. Now that I'm at 0, I'll add on 567, so the answer is +790. Okay? And notice that in effect, if you want to memorize, all you said was, look, I changed the minus sign to a plus sign and changed the sign of this number here. See, in other words, what happened? The subtraction problem became an addition problem, and the -123 became a +123. Now, suppose we wanted to do this in reverse. Suppose we now want to find the directed distance starting at 567, +567, and going to -123. Same logic. You say, I first want to get the +567 back to 0, so I'll add on its opposite, which is -567. Once I'm back to 0, how do I get to -123? 0 plus -123 is -123. So altogether I've done what? I've added on -567 and another -123, and that gave me a -790. And again, to generalize this, if you have m minus n and you want to do this thing mechanically, what do? I first have to replace n by its opposite. See, this does not mean minus here, okay? It does not mean negative, it means the opposite. I first add on the opposite to get to 0, and then to get to m, I just add m onto that, and that's where your mechanical rule comes from, that to subtract You add the opposite, okay? And I've had students come up to me when they get a lot of points taken off on the problem. Let's say the right answer to the problem was supposed to be negative 790, and they got positive 790. And they'll say, why did you take off so many points? All I did was make a mistaken sign. I just thought you'd like to see something interesting. The problem with making a mistaken sign is you'll probably catch it if that was the last step in the problem. If it wasn't the last step in the problem, by the time you've got the wrong answer, you have no idea that there was just a mistaken sign. Let me see if I can give you an example. I call this what a difference a sign makes. Let's look at positive 498 versus negative 498. Obviously, there's only a sign difference. The adjective part is 498 in both cases. And the question is, what's the big deal here? Well, let's start this way. If you see the numbers 4 and 1,000, do you say, oh, I must have made a mistaken sign? How does a mistaken sign give you the difference between 4 and 1,000? Well, watch what happens. Let's look at 502, positive 502, plus positive 498. Since both signs are positive, we simply add the magnitudes. That adds up to 1,000. I picked the numbers conveniently that way. And since they're both positive, the answer is 1,000. Now what happens here? Here the 502 plus the opposite of 498. See, here there's only a sign difference, right? They have opposite signs, so I subtract the lesser magnitude from the greater magnitude. That gives me 4. And I keep the sign of the greater magnitude. That's positive. So the answer now is 4. So in other words, if I stop over here, if you don't see this, this is, oh, I just made a mistaken sign. If this is what I see, you don't see that all I made was a mistaken sign. In other words, by the time you're through with the problem, where you made the mistaken sign can be so far back that you have no idea where it occurred. Let me just pick different numbers at random. Of course, once I pick them, it's not random anymore, so you have to trust me when I say I pick these at random. I'm going to pull two numbers out of the hat. 6 and 92. I'm going to show you how by a mistaken sign makes the difference between getting 6 for an answer and 92 for an answer. Since this is not an algebra course and we don't want to waste time with proofs, let me just give you a cute little device here. Whenever you have two numbers, take half their sum and half their difference. And if you add half the sum and half the difference, you'll get the bigger number. If you subtract them, you get the smaller number. Let's just try it here. The two numbers are 6 and 92. If I add them, that gives me 98. 98 divided by 2 is 49. If I subtract, always the smaller from the greater, 6 from 92 is 86. Divide that by 2 is 43. Look what happens if I take 49 plus 43 versus 49 minus 43. 49 plus 43 is 92. 49 minus 43 is 6. All I did was make a mistaken sign over here, but by the time you see this, you don't notice it. So very, very important, even though it sounds trivial. Don't have students sucker you into giving them more credit because all they did was make a mistaken sign. As long as we're dealing with sign numbers, let's do them right, okay? And I think, again, this is enough for one sitting. Let's go to a practice problem again. I read the problem to you, or you read the problem, you pause the video, come up with an answer, and then resume watching the video to see how I did it and what my comments are. And this is something I should have thought of earlier, and of course, given my old age memory, I might have and forgot that I did. But I'd rather say it twice than not at all. Let me reinforce it this time that one of the best ways to make sure that kids have internalized a concept or a process is don't give them a computational problem. Give them the computation and say, make up a problem where this would have been the right computation to do. In other words, that forces the student to not just look at the symbolism, but to try to analyze what it means. So with that in mind, a practice problem could be using temperature as the model, make up a word problem for which the equation positive 5 minus negative 3 equals positive 8 yields the correct result. In other words, don't just say, I'm going to add the opposite. Tell me a situation where you would be doing this to solve a problem. So I'm going to come back after you've worked on this problem, resume watching the video, and watch my solution, okay? What I wanted to emphasize before I go through my solution was the number of times students will say things like, "I do everything except the word problems." And that's the best indication that what they did was they mastered a mechanical algorithm. They learned something by rote, but had no idea what it really meant. So by giving them the algorithm that they're supposed to use, like 5 minus -3, and asking them, make up a real-life problem where you would have to do that computation in order to get the right answer, is one of the best ways to make sure that they've learned how to internalize it. This is becoming even more important in this technological age, which will probably be becoming even more and more technical. There are now devices that do any computation for you almost instantly. The other day, I saw something advertised. I think it was called a photo camera, phone camera. I forget exactly what it was called. But basically, you scan this over an equation. Not only did it tell you the solution, it also gave you the step-by-step process by which the solution existed. Now, assuming that something like this is going to happen, what is the sense of teaching kids mechanically how to use a rote recipe when all you had to do was give them this new calculator, this new device, and they could get all these answers? More and more what's going to happen is that mathematics courses are going to have to stress the logic, not so much what the recipe is, but when can you use it, when can't you use it, etc. So there are many problems a student could make up for which 5 minus -3 would be the required computation. There's also a lot of wrong ones they could make up, but that's one of the best ways to make sure that they understand what the recipe, the algorithm really is. So here's one I thought of. There could be a lot of different ones. It says in 2 hours, the temperature in the room increased by a total of 5 degrees Celsius. However, during the first hour, the temperature in the room decreased by 3 degrees Celsius. By how much did the temperature change during the second hour? Now, even without knowing the add the opposite rule, a student should be able to say, let's see, it decreased by 3 during the first hour. So it first has to increase by 3 just to get back to no change at all. Then it has to increase by, I should put degrees Celsius in here, but 5 more degrees Celsius to get to 5. See, in other words, you're 3 below where you started from. You first have to make up that 3 degrees, and then you have to make up 5 more. So the answer is what? Positive 8 degrees Celsius. And by the way, there's no credit in solving this problem if the student solved this, if the question was, by how much did the temperature change during the second hour? The answer 8 is not sufficient. First of all, it should be labeled 8 what? Well, 8 degrees Celsius. Secondly, was it an increase or a decrease? You see, the positive sign tells you what? It increased by a total of 8 degrees Celsius. And hopefully this begins to show you the importance of actually giving the kid the answer and having them make up the problem. But at any rate, I think this is enough for today's discussion. Next time we will pick up and talk about multiplication. Multiplication is again straightforward in terms of profit and loss, increasing and decreasing. However, there is one of the operations that really has befuddled people for a long time, and that's why is it that when you multiply a negative number by a negative number, the answer is a positive number? Remember, when we add a negative number to a negative number, the answer is still negative. Why should negative times negative equal positive? And we will unravel that mystery next time. Until next time, though, have fun, study hard. I'll look forward to seeing you soon.